Since when compared to your palm print and iris, okay, iris have the discriminating power when compared to your palm print. Okay, since even if we have taken your the twins, we have the different iris images will be there. We have the more discriminating power for iris biometric trait when compared to palm print. Then I want to give the more weightage for your iris when compared to your the puppet. But how, what weights we have to assign to select the optimum weights for these different biometric traits in a score level fission? We can apply your optimization techniques. We can optimize, okay, the weights assigned for the different the biometric modalities in your score level fission. Okay. At the same time, we can also apply this optimization, okay, to select the different decision rules, okay, which you're obtaining after your decision level fusion. Okay. That means to select either the optimum, the weights we can assign, or the different rules which you are obtaining after your fusion. Okay, at the same time, in your future level fusion, okay, when you are combining the features from the different modalities, different biometric templates, okay, then obviously after your integration, after your the combining these features, the size of the feature set size will be increased. That means initially I have extracted the features from your iris. Okay, for example, I have extracted 400 features from the iris, and I have extracted some, okay, 1,000 features from the palm print. When I have combined these two, okay, 1,000 plus 400, that is, we have the 1,400 number of your features will be there. That means there we are getting your curse of dimensionality problem. We have the more number of your dimensions will be there, the features will be there. Then obviously, okay, in your feature level fusion, to select the optimum features, okay, we can apply the optimization techniques. Okay, that means in different scenarios, okay, in your multi-biometrics fusion level, we can apply these optimization techniques. Okay. If, for example, I will give you some type of the multimodal biometric systems. Here I have given example of the fingerprint, multi-algorithmic fingerprint systems. Okay, we have taken single fingerprint and we have employed your different algorithms to extract the same features. Okay, that means before extracting the features, we have to normalize, we have to binarize, and you have to thin your images. Okay, I have generated your two different thinned images, and then we have extracted minutiae points. Like your minutiae points means, okay, in general, if you observe your fingerprint, we may get your the loops, okay, and there may be a ridge ending points will be there. Okay. Okay, for example, if you observe here, okay, we have, this is called your ridge ending point. Okay, and you have this point is there. If you observe that, where it has been divided into your 2 points, this is called bifurcation point. Okay, there may be some trifurcation point where it will be divided into your 3 points. Okay, like that, we have some points will be there. We can extract those points, that is called minutiae points. We have extracted that have been marked as your blue and red marks. Okay, blue is your bifurcation and red is your ridge ending, like this. This is called ridge ending. Okay, such type of your minutiae have been extracted, and due to some noise, okay, there may be some points, okay, which are outside this particular area, which will be falsely recognized or minutiae points, that will eliminate in your post processing. Okay, that's why we have applied your two different thinning algorithms, and from these two different thinned images, we have extracted your minutiae points, and these minutiae points we can combine. Okay, these minutiae points are features. Okay, these features we can combine in your feature level. Okay, and for example, if we have taken your iris, okay, I have extracted log Gabber features and 2D Gabber features from pre-processed iris image. Since I have applied a 3 by 4 filter okay, a log Gabor filter and 3x4 2D Gabor filter on this iris image. Then I will get the 3x4 log Gabor features and 3x4 your, since I have given the filter size is 3x4, I'll get your 2D Gabor features. Okay, since I have to combine these features in feature level. Okay, this is one feature which I got from your iris. This is another feature which I got for your left iris, and this is for right iris. And then I have to combine. Okay, since I have applied some weighted level feature, okay, these weights, okay, we can obtain either by using your any optimization algorithm, or we can manually give these weights. Okay, and I have given your the weighted feature level fission, and then I have applied your horizontal and vertical downsampling, and now I can convert your a normal vector. This is my feature vector. Okay, this I can use it for your matching purpose. Okay, otherwise, for example, if you are taking your from the same iris, okay, from the left iris, I have applied your some Gabor filter of size 3x4, and for the right iris I have applied the Haar wavelet. I have applied the
329.90. Now you can do.
okay, I have applied the Haar wavelet to extract the features. Okay, then if you observe that, okay, the Gabor features is different from your Haar features, since they are different domains. Then I have to apply the normalization before your integration. That's why we have applied your downsampling, and then we have converted your vector and normalized. And here also the Haar wavelet, Haar features have been normalized, and we have combined. Then obviously whatever the this features which we got after your integration, which will be of high dimensional feature space, like your, this is an example. Okay, we have the iris is there, okay, which we have identified your x and y derivatives, gradient and non-max suppression. This is of all your pre-processing images, and also Gabor features, and also the feature level fusion of this particular. This is your the Gabor features, and this is your log Gabor features, and the integration of these two features. Okay. Then obviously we'll have your the more number of your the features will be there. Okay, we'll see one example of your optimization technique in your multi-biometrics, that is feature selection. Okay, we have seen, okay, we can select either the weights, or we can select your the different rules which are the optimum rules in your decision level fusion. Okay, but here I am discussing about one example called feature level fusion, and in this feature level fusion, how we can apply your optimization techniques, okay, as a to select your optimum features in your multi-biometric systems. Okay, why you are selecting evolutionary computations? We have a lot of your techniques are there, feature selections. Okay, but these whatever the traditional feature selection techniques are not suitable for your multi-biometric systems, as they require your the previous knowledge about where we are applying all these things, and we need to identify the what are the constraints, and okay, we need to take your whether you are accessing with your non-linear and linear data, where it is linearly separable, non-linearly separable data. And these are all the things that we read in your traditional approaches. Okay, backward selection or forward selection like this. But these are all the things that are not required in your the evolutionary computation based your optimization techniques. Okay, we have a lot of your evolutionary computation, that is optimization techniques like your genetic algorithm, your particle sum optimizations, cuckoo search, your anti-colony optimization, artificial beacon. Like we have the different firefly or optimization or whale optimization. Like we have the different optimization techniques are there, and these optimization techniques we can employ as a feature selection after feature level fusion in your multi-biometric systems. But we'll see, okay, the particle sum optimization and how we can apply this particle sum optimization for the feature selection. Okay, this particle sum optimization is one of your the best algorithm, okay, which have the global searching capability when compared to your the genetic algorithms or genetic programming or ant-colony optimization or whale optimization. Okay, when compared to these optimizations, okay, this have your the more the global searching capability, and at the same time this PS will have the memory capability where the particles in your particle swarm optimization, that will hold the information about your the best solutions around this best solution around. They can memorize the best solutions, nearby that. Okay, that means in your biometric systems, main thing is your the space and the time is your the main constraints. Okay, since when you are employing a biometric devices, okay, we need a less amount of your space to store your template, and within short time we need to authenticate that. Okay, that means when you're applying your optimization technique for feature selection, okay, your PSY is your less expensive, expensive because of whatever the mathematical computation is there. Within less time, we can compute, and which requires your minimum memory space to perform the feature selection, to perform your feature selection. That's why this will be one of your the best feature selection mechanism we can apply in your optimizations for your multi-biometric systems. Okay, and obviously this particle swarm optimization is completely or the based on your the birds flocking behavior. Okay, what are the birds here we have seen? Each and every bird will consider as a one particle in our problem, and these birds will search for the food. Okay, and once they have identified them, that means they will move around. I mean, they will search in different spaces and they will try to look for your food. Okay, whatever the food, for which food they are searching, that is called our solution for our problem. Okay, that means whatever the solution we want to find, that will become your food. And these birds are becomes your particles in our problem, and this will search for this best solution. And once a bird has identified a solution, identified a food, it will remember that. Okay, and this knowledge will be shared to all other birds. That means each and every particle will try to identify the best solution. That means it will try to identify the food locations. It will try to identify the food locations, which will call it as your best solutions, and then try to memorize these locations, this solution, and this location information, food location information, will be shared to all other particles. That means all other birds, and based on this, okay, they will try to identify which is the best location. Okay, among all other locations gathered by the different birds. Among that, you'll pick up your the best one. You pick up your the best food. Okay, like that, this particle swarm optimization will work. Okay, that means each and every particle, okay, it will identify whether whatever the location, the food location the bird has identified, whether it is a good or not. It will quantify all these things, how much it is there. Okay, it will compare against with all other particles, all other birds information. Okay, then once we have identified the best one, okay, it will try to imitate all other in that same the best one by all other new particles. Okay, then we'll see. Okay, in any particle swarm optimization algorithm, okay, we have the very different particle swarm optimizations algorithms are there. Okay, the first step in any particle swarm optimization is you have to identify the particles, that is your population. Okay, we have to encode your the particles, and you have to initialize your the particles, that is population. Okay, since here we are applying your the particle swarm optimization for the feature selection. Okay, our main goal is you are applying for your feature selection. When you are applying for the feature selection, each and every particle is one solution. Each and every particle is our one solution. Okay, then what is our solution? Our requirement is we have the n number of your features are there, which is extracted from your different biometric modalities. Among those, you have to select the best features. We have to select your the best features. When you have the n number of your features, you have to select the best among these n number of your features. Okay, then in this one, each and every particle will become your the size of the particle will become your the number of your features. If you have n number of your features, after your integration of the features from the different modalities at feature level fusion. Okay, then the n will be the size of your particle. Okay, then you can take any number of your particles. Okay, any number of your, either 10 or 20 or 30. Okay, in general, in most of your problems, 10 to 50 is your population size. You can take 10 to 50 particles. Okay, each and every particle is your a sequence of your the binary bits. Okay, in our feature selection problem. Okay, 1 indicates that the feature has been selected, 0 indicates that the feature is not selected. 0 indicates the feature is not selected. Okay. And then once we have initialized all the particles, the population, then you have to compute the fitness of your each and every particle. Okay, that means we can define your the fitness function, and based on this fitness function you have to identify the fitness score of each and every particle. Okay, this fitness function is your objective function, okay, which will minimize or maximize, okay, your constraint or the function. Okay, here we want to increase your the fitness value, or we want to decrease your fitness value. That depends on what fitness function you have designed. Okay, and once we have calculated your fitness values of each and every particle, then you have to update your the global and local positions of your each and every particle. Since each and every particle has identified the best location, that is the local to that particular particle. Okay, and in that population of your particles, you have to identify the global position, the best position. Okay, the particle one has given the best solution. Okay, with respect to particle 1, particle 2 has identified the best solution with respect to particle 2. Like all n number of your particles have identified their best solutions with respect to their position. Okay, then that is a position with respect to, that is a local position. Okay, local value with respect to the particle, and among those, which is the best one, that is the global solution among all the particles that we have to identify.
Madam, please unmute your mic. Madam, please unmute your mic.
Sir,
Hello, madam.
sir,
Please unmute your mic.
sir, myself is in unmute only.
Okay, madam.
Okay, once we have picked up your the best solution, then each and based on this location, each and every particle will try to move in that direction to identify the best one, since the particle 1 has identified the best solution, best position, and particle 2 has identified some other best solution, and particle 3 has identified the some other best solution. Okay, among these 3 we have picked up the best one, and the remaining all, they have to move towards your the global, the best position, the food location or solution. Okay, then they have to move towards that one. That means they have to update their velocity towards that particular the best one. Okay, we have to update those velocities after that, and then you will get your the new particle positions, once the particles has moved towards your the global solution, and then you'll get your the new solution and new particles, and again will compute your the fitness value for these new particles, and again you will update your the global and the local the best positions, and again you will try to move towards your the global position by updating your velocities, and these 2 to 5 steps will repeat until you terminate your that particular algorithm. That means until we'll put that, okay, once we have reached that particular criteria, okay, we have identified that the best value. Okay, once we have completed your 50 iterations or 20 iterations or 30 iterations, that may be one termination condition in general in any optimization algorithms. Otherwise, we'll put some criteria. If your fitness value is between this, okay, less than this one or greater than this one, then also we can stop. Like that, we can identify the termination condition for any optimization algorithms, and once we reach the termination point, we can stop, and whatever the global position we got, that will be your the solution, and that we can give simply Okay, and in this one, first we have to initialize your the particles, your populations, and then you're updating your positions based on your fitness value. That is, okay, you're finding your new particle fitness value. You have to update your the global and local positions, and then okay, we have to repeat the same process. Once we have identified the global best position and whatever the best solution we got, the best solution we got, that best solution will consist of your ones and zeros. The one indicates that the feature has been selected, zero indicates that the feature is not selected. Like that, we can extract your the essential and the optimum features by using this your PSO. Okay, for example, okay, the first step is you have to initialize your population, or you have to encode your particles and populations. Okay, here each and every particle you can represent by P. Okay, we have the P. Okay, I have n number of your features in my template, biometric template after feature level fission. Okay, then okay, I have to place okay here n number of your okay n number of your position. That means this is single particle, a particle I, okay, which have the size is your n. Each and every p1 indicates the first feature, p2 indicates second feature, like your pn indicates your last feature. Okay, and this is your velocity of your particle, velocity of your the particles. Okay, and now I have to initialize each and every particle as your ones and zeros. Okay. Simply based on this velocity, based on the velocity, okay, I can encode the particle by using your sigmoid function. This is one example. We can use any of your the methodologies to encode your particle. I have used okay sigmoid function I have applied to the velocities to encode your each and every particle, to encode each and every particle. Okay, then I will get your one particle. Like that, I will assign your different velocities for initialize different velocities for your different particles, and based on these velocities I will encode your the each and every particle in the form of your ones and zeros. Okay, and once we have initialized that, I have to calculate my fitness function. Okay, once I have calculated the fitness function, I have to move the particle from okay, this is the particle position, p1 position. Okay, and this is your the particle 2 position, and this is your another particle 3 position. Okay, these three I have identified the best solutions in this one. Okay, okay, and we have another called p4. P4, okay, among p1, p2, p3, p4 has identified the best solution, food location. Then you have to update the velocities of your p1 and p2 in such a in such that okay, they have to move towards this global solution. They have to move towards this particular global solution. Okay, then I can update my particle position either if it is one. Okay, it is your encoding. Okay, I have to update this the velocities of this particle, and in such a way that they have to move towards your the best one, they have to move towards your the best one. Okay, then I can use this function okay to update my the particle velocity. Okay, that means previously this is the ith particle in kth iteration. In kth iteration, this is the velocity. Okay, then in the next iteration, we have to update the velocity. You have to update the velocity. Okay, whatever the previous velocity is there, whatever the previous velocity is there. Okay, and this is your inertia weight. This is your inertia weight, and this is the constant which we can define. Another one is okay, this is your the self knowledge, and this is your social knowledge. That means based on the current position which has been identified the particle, its own particle, that is your self knowledge, and based on the global optimum play, that means which we have identified from all the particles. Okay, we have to update your the velocity. You have to update your the velocity. Okay, that means you have to move in a particular direction. Okay, in which direction you have to move. That will be given by your alpha, that is called inertia component, will decide, okay, in which direction I have to move. And the second one will identify, okay, what is the best location which we have identified till now by the particle itself. Okay, that is the memory capability, that will be given by your second component. And third one is, you have identified the best solution among all other all other particles, all other the birds. Okay, and based on this global one, okay, you are trying to move, you are trying to change your velocity, you are trying to change the direction, the particle direction. That means while the particle is updating its velocity and its direction, it is considering its own component and its own identification of your the best location, and it is also considering the best position identified by the all other particles. Okay, it is sharing the information, it is identifying it is keeping its own best solution, and based on this it is identifying your whether it has to move in which direction. And once it has been identified, will generate your new particle. Okay, but before that we have to calculate your fitness function, and once we have updated the particle positions, we'll get your new particle, and that fitness function also we have to calculate, that fitness function also we have to calculate. Okay, then once the particle is updated, okay, again you have to calculate your fitness function. But in this example, okay, we are discussing the PSO with respect to the feature selection in multi-biometric systems. Okay, and in this multi-biometric systems, we have identified that, okay, we have collected the samples from your the biometric trait 1, the biometric trait 2, and we have extracted the features, and we have combined at the feature level fusion. We have combined at your feature level fusion. Okay, then, okay, if I have considered, for example, my first biometric trait is your my fingerprint. Okay, and second is your my iris. Okay. Then I have extracted the features vector, that is features from your fingers, and I have extracted the feature from your my iris. Okay, and these features I have concatenated in feature level fusion. Okay, then what should be my goal when I'm designing the fitness function in selecting your optimum features, Okay, I have to select the best features from both finger and iris in such a way that I have to accurately authenticate or recognize the person. I have to accurately or authenticate or recognize my person. That means, okay, we have some features, okay, which have the more discriminative power in fingerprint, and there may be some features which have the more discriminative power in iris also. Okay, that means when you have collected the features from your fingerprint, there may be some features which may be matched with some other person's features. But there are some feature points, okay, which are unique to this person when compared to all other persons. Those are called discriminating features. For example, if you observe that your finger, okay, you'll find your loops, okay, a circle, okay, or you'll find your the bifurcation point that may be different. The position of that bifurcation point may be different from one finger to other finger of the same person, or the different fingers of your different persons. And those points, okay, the critical points which have the more discriminative power, okay, that we have to identify. That is the main goal of your optimization technique, selecting your features, okay, in your multi-biometric systems. Okay, then obviously, okay, we have to consider one factor as in your fitness function. What is the recognition accuracy of your the biometric data? Okay, with these selected features, okay, how much accurately you are able to recognize the person, the person. Okay, that will be the main component of your fitness function that you have to increase. Your fitness function may be a maximization function or it may be a minimization function. Okay, in this optimization, that means when you're applying your PSO for your feature selection multi-biometric system, we are considering your accuracy as one component in your fitness function. Okay, when you're considering the accuracy of that particular sample, with respect to that sample, then obviously we need your more accuracy, okay, with respect to those features, then obviously you are going to maximize your fitness function. Your fitness function is your maximization problem. Okay, and here what are the fitness function I have given in this example is your, which consists of your three components, alpha, beta, and gamma. Okay, alpha is your one component that is called accuracy of your biometric data. For example, where I have given 14 features are there after your concatenation of your finger and iris, for example. Okay, in this I have given 1 1 like 0, okay, 0 1 like that I have given. Okay, the best particle one. Okay, this is my particle. For this particle I have to calculate my fitness function. Okay, now one indicates that this feature have been selected and this is feature has been selected, this feature is not selected, and this has been selected. Okay, and okay, and whatever the features which have been selected, we'll consider only those features, and based on those features we'll try to recognize the person. If you're able to correctly recognize the person, okay, then how accurately we are able to recognize. If you have n number of your different persons are there, okay, how many of them you're able to recognize correctly, that is recognition accuracy. That is your the first component in your fitness function, okay. And next one is your the beta indicates, that means we have some features have been selected and some features have been not selected, but this is not the best one. What are the features we have selected till now, okay, in the initially, okay, that may be a best one or that may not be a best one, but what is the impact of those selected features, okay, that you have to consider. Okay, at the same time, since this is not the best solution, what are the features which have not selected, okay, that also have some impact on your this recognition accuracy, I mean on your multi-biometric system based authentication. Okay, that is your third component. Your beta will give the impact of your selected features and gamma is giving your the impact of your non-selected features. Okay, that means the combination of all these three will combinedly will correct as your the fitness function, okay, which we have designed in this example. Once we have calculated this fitness function, okay, for example, how you can calculate accuracy here. Okay, that means we have the database is there, okay, where we have stored all your n number of your the person details, the templates, first person information, second person information, like that. Okay, now we got your new features, okay, and you want to identify, okay, the person who belongs to this particular feature vector. Okay, then obviously, okay, among these what are the features which have been selected, and those features we are going to use, and in this database also we are going to use those features to compare against with all the n number of your person samples, and you want to check whether they have been matched or not. Okay, then obviously, okay, how we can match this one, either we can use your the normal distance based matching, or we can use your the machine learning algorithms here. We can use any machine learning algorithms to match and to identify the accuracy of this particular match. Okay, and in general the best suitable machine learning algorithm is we can go for either support vector missions, or we can go for your the decision C 4.5 decision tree algorithm. Okay, and in general, these two will give your the best results. Okay, when you are trying to find out your the accuracy. Okay, in your fitness function. In general, in your classification of your multi-biometric systems, okay, we can go for your the machine learning based your the classification or machine learning based your prediction of your accuracy while calculating your fitness function. Okay, here we can apply your the one of that particular algorithm to calculate the accuracy with selected features Okay, then second component we are calculating your what is the impact of your the selected features. Okay, NDB means how many number of your the total number of your biometric samples we have collected. That means we have collected from your 100 people or 1000 people. That is your database size. And N is your what is the total number of your features are available. Among those, how many features have been selected? How many features have been selected in this? Okay, this is your second component. And your third component indicates your non-selected features. Third component indicates your non-selected features among n number of your features out of your n number of your the biometric images. Okay, once we have calculated your fitness function, okay, then you can identify the best one. Okay, we have can identify the best one. Okay, we can update your the global and local best positions, the local and the global best positions. That means we have particle 1, particle 2. I have selected my population size as your 5. Okay, and the particle size is equivalent to 10. Since after feature level fusion, I got my 10 features. I got the 10 features. Then my particle size is equivalent to your 10. Okay. And I have initialized by using my sigmoid function. I have encoded each and every particle. And I have calculated your fitness function. I have calculated your fitness function value for each and every particle by using my this fitness function. Okay. Fitness function. This is my fitness function. Based on this, I have calculated, and based on this, applying your sigmoid function, I have encoded my particles. I have encoded my particles as 1 or 0, and I have initialized. I have initialized. Okay. Once I have initialized, I have calculated your fitness function. I have to update my particles positions. I have to update my particle positions. Okay. And based on this, I can update my particle positions. But when I am trying to update these particle positions, okay, what should be my alpha and what is this C1, what is this C2 and all these things. Okay, this alpha is my inertia component. Okay, this is one parameter which I have to set. This is the inertia weight, okay, which always provides you the memory capability for a particle. Okay, that means in general, you can in most of that means by applying your a lot of your the studies. Okay, initially it has been set to your 0.7. Okay, we can set between 0 to 1, any value 0 to 1. Okay, but okay, in our example we have set it has to 0.7, and after this, okay, we are updating this inertia weight in in every iteration. Each and every iteration we can update this inertia weight, okay, which will range from your 0.4 to 0.9. Okay, that also we can change, Okay, and we have a cognition and social parameters. C1 is your the cognition parameter or memory parameter, and C2 is your the social parameter, okay, which are also the constants, okay, which has an impact on your the convergence speed of your the algorithm. Okay, how fastly we the convert, that means we the algorithm will converge to your the global solution, that will be decided by your C1 and C2. Okay, the best solution for C1 and C2 will be is in general C1 plus C2 will be 4. Okay, that will be the best solution. Okay, we can have in general in this example I have taken C1 and C2 as your 2. Okay, Is it clear? Okay, that means we can also select your C1 as your 1.7, 1.8 or 1.9, any values. Okay, the best solution is your C1 plus C2 must be a 4. Like that, we can take this particular values. Okay. And once we have updated this particular positions, okay, then you have to pick up. That means, okay, you got your the new particle positions. Okay, that means initially we have calculated your, you have encoded your each and every particle, you have encoded your each and every particle, and you have calculated your fitness function values for each and every particle by using your the fitness function, by using your the fitness function. Okay, among these, okay, you have to identify what is the global the best position. This F1 indicates the best solution, the best value with respect to your the P1. F2 indicates the best with respect to P2. But with respect to the complete population, your P1 to P5, what is the best one? For example, you'll consider fitness means you are considering your accuracy, the impact of your features. Then obviously our fitness function is your maximization. The maximum value will become your the best one. The maximum value will become your the best one. For example, among this, okay, particle 3 is the maximum, the best value. That will call it as your the global best position. The global best position. And this F and your F1, your F2, F3, F4, F5, whatever the particle positions, these are called your the local solutions, the best positions, local best positions. Okay, after you're updating this, after you're updating to your the new velocities, okay, your v1 dash, v2 dash, v3 dash, okay, you have to again calculate your the fitness function. You have to calculate your the fitness functions. You have to calculate the fitness functions. And now you have to compare. Previously the fitness function is your f, and now the fitness function is your f1 dash. Okay, which is the best one? Which is the best one? Okay, that means since it is the maximization, if f1 dash is maximum, then the local best position for p1 will become your f1 dash. Otherwise, f1 will become your the local best position, and you will discard your the new position, new fitness value, that is your f1 dash. Like that, okay, you'll try to compare your each and every particles here, the previous position and the current position, and you'll try to update your what is the best local position with respect to each and every particle. And once we have identified the best particles local positions, okay, we'll try to identify, okay, the global best position, current local global best position, and we'll pick up and we'll compare against with the previous global position, the previous global position. The current global position, if it is the best one when compared to your previous global position, then you will update and will go for the next iteration. Otherwise, will not consider the previous, the new global position, will continue with the previous global position, and again will update. That means each and every time you are the particle is updating its position with new velocity, and it is calculating your the new particle position. New particle will be generated, and this new particle fitness value will calculate, and that will be compared against with previous value. And if it is the best one, will update. If it is not best one, if it is not the best one, will keep with your the previous position only. Like that, each and every particle, they will update their local positions. By that, will update your the global positions in that iterations. Okay, in each and every iteration will do. Okay, then once the required number of your iterations have been over, that means if I have set your 20 iterations, after 20 iterations, what is my global best position? Okay, whatever the global best position means your particle itself. What are the particle we have encoded? That is, okay, in this particle I have ones and zeros will be there. This will indicate that whatever the features we have selected, then what are the features which are not selected, which are not optimum features, and those features will select and will create your the features for complete your the database with these selected features, and those will use it for your the recognition of the person, recognition of your the person. Okay, just I'll give you some of your the results, okay, which we have seen. Okay, we have developed your multi-algorithmic palm print recognition systems, fingerprint and iris. Okay, that means on the palm print we have applied your two different algorithms, okay, to extract the features, and those features we have combined at feature level. Like your fingerprint also, I have applied your two different feature extraction techniques, and whatever the features we have extracted, that we have combined. And also from the iris also we have extracted your two different features from your two different algorithms, and those we have combined in your feature level vision. Okay, there we have tested on your Casio database. We have the palm print database and iris database is there. IIT Delhi palm print database and iris database, and also FEC fingerprint database and Casio database is there. Okay, those databases have we have taken, and in these databases, okay, we have uh, without feature selection. Okay, after you're integrating the features from two different algorithms on your palm print, we got the feature set size is 10,000. Okay, after concatenating the palm print features from the algorithm 1 and algorithm 2, okay, this algorithm 1 and your algorithm 2, okay, that once we have integrated this from the size of this feature, number of features are your 10,000, okay, without any feature selection. And once we have applied your the PSO, particle swarm optimization, for the feature selection, okay, the feature selection feature size has been decreased to 2602. That means among 10,000 features, okay, 2,602 features or have been selected as your essential and important features from your palm print in Casio database. Okay, in your IIT Delhi database, okay, again we got from algorithm 1 and algorithm 2, okay, 10,000 features after your feature level fusion. And once we have applied your particle sum optimization, we got 2,413 features as an essential features, okay. Like we have developed your the different fingerprint systems, okay. Like this is the one fingerprint system where we have applied your different algorithms, okay, and another fingerprint system where we have applied your different algorithms for extracting your features, okay, on same databases. Without feature selection, how many features, that is one or two features are there. After feature selection by PSO we got 29, okay. And the same time, if you have applied your iris, okay, we have the three different algorithms we have applied. One is your 2D Gabor filter and log Gabor filter and Haar wavelet for the feature extraction from the iris, okay. And we have combined 2D and log Gabor, that is your one biometric system, and another one is your the log and Haar, that will be your one biometric iris system, and 2D Gabor and Hard, that is another iris recognition system. Like that, we have designed your three different multi-algorithmic iris recognition systems. Okay, and we have tested, and in all this, okay, we got your the sample size is your around 4,900, 4,800 to 4,900. And after feature selection by your PSO, it has been reduced to your 2,100 to 2,200, 2,000 to 2,200 in different algorithms, in different algorithmic systems. Okay. But once we have identified, okay, what is the effect of this feature selection, why you are applying this, okay, that means if you want to process 10,000 features, it will take a lot of your time, okay, and you have to store all the 10,000 features. That means you need more memory to store a single biometric template which is of your 10,000 features. And when compared to this, if you want to store a biometric template of your size 2,602, then obviously the size has been reduced by 5. Then the memory size consumed by the feature vector with respect to your, the palm print is very less when compared to your without feature selection. And obviously, if you want to verify all the 10,000 features, and if you want to decide the result whether the person is a genuine or imposter, it will, you have to verify all the 10,000. It will take a lot of your time when compared if you want to verify only 2,600 features. That's why, that means if you have applied your feature selection, okay, the time has been reduced, and also the time has been reduced, and also your, the space is also, requirement is also very less. And these some examples, okay, where you have combined your palm and finger, okay, different, okay, we have collected here different databases, okay, for the palm print and fingerprint, and different algorithms we have applied to extract the features from the palm print and fingerprint. And you have developed the different combination of your palm print and fingerprints, okay, where the sizes of your, after your feature level fusion of this palm print and fingerprint, we got this different sizes in different systems based on the different algorithms for feature extraction. 10,060, 10,050, 10,048, 10,000 your 52, like that, of different sizes. When we have applied your particle swarm optimization for the feature selection, okay, it had been reduced to 2,600, 2,200, 2,300, like that, the size has been reduced. Okay, with this reduction in the size, okay, without feature selection, if you apply that okay, recognition, the recognition accuracy is, okay, the recognition accuracy is only up to your 80 to only 92% only, the recognition accuracy. But once you have applied the feature selection with respect to your PSO, it have been, okay, increase it to your 94 to your 98 percentage of your, the accuracy we got, okay, with respect to your, the SVM based your classification, and C4.5 based your classification. Okay, here we have applied your PSO. We can also apply your artificial bee colony algorithm, or we can apply your, the cuckoo search algorithm, or we can apply your whale optimization algorithm. Okay, we can apply any different optimization techniques. We can apply, we can apply, okay, for selecting your, the features in feature level fission, or selecting the weights in your score level, weighted score level fission, or selecting the rules in your decision level fission, selecting the rules in your, the decision level fission. That means, for example, if you want to apply your in score level fission to select your weights, then what should be your particle? Okay, what are the different components which you are considering to decide your weights, and those will become your, the particles. Here in this example, we are considering your, the features as your, the part mean, okay, the particles, okay, the particle is encoded in terms of your ones and zeros. We have applied your binary PSO, okay, ones and zeros, and these will indicate your features. But the same PSO algorithm, if you want to apply for the, to calculate your, the weights in score level fission, the weights in your score level fission, then to estimate these weights, what are the components which you are using in your biometric systems, and those components will become your, the particles while you're encoding. And based on this, you have to design your own fitness function. The remaining steps are same, how we are encoding, okay, that is different. And the parameters, your alpha, inertia weight, your cognition parameters C1 and C2, and these will vary, okay, from problem to problem. You have to decide which one is the best one, okay, and then you have to design your own fitness function. Since there the problem is different, the problem is you're estimating the weights, okay, then there you have, what are the factors you are considering. Based on those factors, you have to design your fitness function, you have to design your, the fitness function, and we can apply your PSO for estimating those weights also. Okay, not only this, okay, here we can apply this in general. Nowadays in your biometric systems, okay, we have to we are using your, we have a lot of your the presentation attacks are there. Presentation attacks means, okay, we are using your the temporary or the photos or videos or the paper one, or whatever the, I mean, the rubber things, the face masks which you are using at the time of your authentication. Okay, there we have to identify whether the person is who have in front of your sensor, okay, who is giving the biometric template is the living person or not, that you have to check. Okay, there when you're acquiring that when you want to detect the presentation attacks, there we can apply your the optimization techniques. Okay, whether the particular whatever the biometric template we are giving, the template is whether it is a living person that we are acquiring from the living person, we are acquiring from the mask or any paper or any of the rubber part or any silicon component which you are using to give a biometric template to detect the type of your presentation attacks. Also we can apply your optimization techniques. This is going on research we can use. Or okay, when you are using this, if you want to increase the performance of your the still the biometric recognition, okay, in pre-processing and in your feature extraction also we can use the optimization. We can use your the optimization while you are selecting your, okay, the pre-processing. For example, in your fingerprint you have to segment the area from which we want to extract the features. Okay, in that segmentation you can apply your optimization, you can apply your optimization technique. Okay, and also when you are collecting your the samples from your different sensors, okay, you have the different biometric sensors are there. Okay, if you are not using the best sensor, then obviously whatever the template you are getting, that may not be of your good quality, and obviously the recognition accuracy will be very less in your systems, in your multi-biometric systems. Then obviously we have to get your the good sensors. Okay, that means, okay, these sensors will okay, will be used, okay, in avoiding your presentation attacks. In your presentation attacks, that means whatever the biometric capturing devices, okay, whatever the software we have written, okay, when in the sensor itself it will identify that whether the person is a living person or we are extracting, we are getting your template, the template from your some paper or the video or that thing. Okay, that means when your authentication time, if you're instead of your face, if you're putting your the photo or the photo in your mobile or some video or a normal paper photo, if you are placed in front of your sensor, okay, the sensor has to recognize, the sensor has to recognize you are trying to capture the data from your non-living thing. Okay, that is called presentation attack. Okay, in your sensors itself, okay, while you're designing your sensors itself, in that also we can incorporate this optimization technique to detect that particular attack. Okay, now thank you. If you have any queries, you can ask.
No. మళ్ళీ చెప్తాను. Capital B, small o, SU. @1987. Any queries from authors?
Good evening,
Any
ma'am.
query from authors?
Good evening, madam.
Manish Gaikwad. Please tell.
Madam, if you are doing this biometrics research, so multimodal biometrics, especially when it comes, so we need to take the data of different biometrics of same person, right?
Madam, generally, okay, you can take, you have to take different biometrics from same person, but for our research purpose, okay, you can create your database for your multimodal systems. Okay, whatever the iris we have collected, that may be from your different person, and whatever fingerprint we have collected, that may be different person. But at the time of your enrollment, okay, you have generated a template.
Okay.
From person 1 and person 2, I have collected iris and finger, I have combined and I have generated a template.
Okay.
Okay, at the time of your verification or identification also, I have to collect the same iris sample from the person 1 and same finger sample from the person 2, and I have to combine and I have to verify.
Okay.
Okay.
Okay. So it is need not that it should be from the same sample, same
Yes,
person.
same person.
Okay. So if we are searching for multimodal biometrics online dataset, we are not finding it out. So
We won't find in it won't
yes,
have.
madam.
You have
Yes.
to consider from the different persons.
Okay, madam. Madam, any other research areas, research ideas can you give in this multimodal biometrics?
Okay, the main thing is your madam, you have to identify presentation attacks.
Okay.
Okay, and next one is your you have to provide the security for the biometric template.
Okay.
Biometric security and presentation attacks, and one is your liveliness detection. These three are your the present area of research in biometrics.
Okay. And user authentication, madam. What about the user authentication using this multimodal biometrics?
User authentication based on the multimodal biometrics means that is already over, madam. From the last year 10 years, okay, that is already going on. But the main thing is your you have to identify your whether you are capturing your data from your the living person or not.
Okay.
Okay.
Okay, madam.
And one thing is from the biometric template which you have gathered, we have to identify the age and also the gender.
Okay.
Okay, this is another research, but it is a little bit one. The main thing is your the living or non-living, and the attacks is
Okay.
the major research in your biometrics.
So attacks in the sense, madam, I didn't get it.
At presentation attacks means that's why I have given in front of your sensor. Okay, you are using a face recognition system. Okay, instead of your face, okay, you can place your photo.
Okay.
You can place your video. Okay, since you want to identify whether the living or non-living, okay, by moving your eyes, okay, you can identify that the person is present in front of your camera. Then simply we can record our video and we can place the record in front of the sensor.
Okay.
But that is not originally the person. It is a video has been played.
Yes.
That you have to detect.
Okay. So to identify whether a person is living or non-living, what are the different techniques we have, madam, in general, but what?
That depends on the biometric trait you are using.
Okay. So if we are going for identifying whether a person is living or not, we can go with single unimodal biometrics only, right, madam?
You can go with unimodal biometrics.
Okay. Do we use any deep learning approaches in this for identifying living?
You can use your deep learning approaches for your recognition and also for feature extraction, or we can use combination of your the image processing based feature extraction along with deep learning based feature extraction.
Okay, madam. Thank you very much.
Anyone? Anyone? Anyone of there? Any queries from others? Okay.
Sir,
I-
can we get the recording of the session?
Yes, madam. I will share you everything, including YouTube links.
Okay, sir. Okay, thank you.
Aruna madam, thank you very much. I'm audible, madam.
Yes, sir, you're audible, sir. Thank you.
I'm extremely thank you, madam. I would like to express my view, sincere thanks, gratitude for your outstanding keynote address on optimization techniques in multimodal biometric system, especially your focus on biometrics, including security areas at the third International Conference on Machine Learning and Big Data Analytics, ICMLBDA 2023. Your expertise and insights truly captivated captivated the audience and left the lasting impact on all who are attended. Your presentation was exceptionally informative and thought-provoking. The manner in which you explained complex concepts with such clarity and enthusiasm really truly remarkable, madam. It was evident that you possess a deep understanding of the subject matter, especially biometric and password authentication mechanism, and your ability to communicate it efficiently, effectively was truly impressive. Furthermore, you have your comprehensive, elaborative exploration of optimization techniques in multimodal biometric system provided valuable insight into the challenges and technique can be applied into the real-time world scenarios, which has undoubtedly inspired many attendees to explore the desired areas furtherly. And once again, I would like to express my heartfelt gratitude for your invaluable contribution to the conference as a keynote speaker. Your expertise and passion have undoubtedly l- left a lasting impact on all attendees, including myself also. Thank you for your sharing your knowledge and for inspiring us to explore new frontiers in the existing field. Wishing you continued success in your endeavors, madam. And I hope to have the opportunity to attend another one of your enlightening presentation in future conference and events also.
Sure, sir. Thank you. Thank you so much.
Thank you very much, madam.
Thank you, madam.
Thank you very much, all of you participations. On 6 o'clock onwards, you will present your paper presentation as per schedule. Please contact your session chairs immediately. Those give session chair links, presentation links. Okay, please contact your session chairs along with your groups. Thank you very much.
Thank you, sir.
Okay, sir. Thank you very much.